All right, good morning, everyone. Good afternoon, wherever you are. Welcome to today's webinar. I will be discussing and presenting to you on the SCS siting tool, taking the guesswork out of continuous monitoring solutions, deployments. I'm Thomas McArthur, Director of Operations here at SCS. I've been with Kuva for the past 8 years and SCS since the acquisition last year. I've got a background in chemical engineering. So I will start out. So what are we going to learn here today? What are we going to cover? What should you walk away from this with by the end of it? So what is the siting tool? What does it do and how does it work? What are the variables that impact detection capability? What are the performance metrics we use to quantify a sighting, and those are coverage and time to detect? How do you quantitatively compare technologies and configurations? And how can you get your sites configured and evaluated? So let me just double check to make sure everything is working. It appears so. Okay. So let's start with a day in the life of one of your sites, or in this case, we've got a quarter. This is from an actual site, and you can see we've had 2 inspections over a 3-month period. Each survey is a good, careful measurement. The first one, you detect virtually nothing, and then the second one, you pick up significantly more. So you close out the quarter and you report the average. Based on what you saw, it's defensible. However, this is what was actually happening at that site. And while the average may tell a part of the story, as you can see, a lot more happened throughout the quarter. So this isn't a criticism of surveys. Drones, flyovers, and OGI surveys are excellent at what they do. They cover a whole site quickly, and they localize what they find. The gap isn't in detection, it's in temporal coverage. 2 snapshots out of a 90-day period is just that. It's just 2 frames in an ever-evolving film. So this puts the operator in a bit of an uncomfortable situation. You can't fix what you never saw, and it's hard to defend an inventory built on a couple of data points when reality is as variable as this. If you're heading towards OGMP 2.0 level 5 reporting, you're being asked to reconcile site level measurements with your bottom-up numbers, and this picture here is exactly one reason why those 2 don't line up. So the question stops being, what did we see in these surveys? And it becomes, what happened between surveys? And that's what continuous monitoring answers. But it does introduce a number of other questions. So why might you be interested in continuous monitoring? Could be that your periodic surveys have variable results and you want to understand the intermittency of the emissions. You want to know about the emissions as soon as they happen so you can fix them much sooner as opposed to every 90 days. Or you're interested in site level inventories, for example, for the purpose of OGMP level 5 reporting. So what are some considerations? There's a lot of things you have to take into consideration when you're going to deploy continuous monitoring. A lot of questions come up, such as what technologies make sense? What kind of sensors will get me the results I want? How many sensors do I need to achieve the desired performance? And how do different setups compare, and why specific geometry and weather is important? lastly, how do I determine that all my sources are covered from a single deployment? So this is why we built the siting tool. So what is the siting tool and what does it do? It implements an easy to use and systematic procedure to establish how well a sensor layout can detect methane emissions from potential sources at a specific site. It calculates key performance indicators like coverage and time to detect for all potential sources based on the sensor layout, site geometry, historical weather conditions, a detection model, and the sensor characteristics. And what does it facilitate us to be able to do? Obviously, number one is it facilitates us siting to determine and optimize the number of sensors and their position to achieve desired performance. It allows us to communicate in a transparent way the expected performance to customers and other stakeholders. It allows us to compare one technology to another and to compare from one site to another to make sure if we do have numerous sites, we're achieving generally the same level of performance from a configuration. And it provides a defensible record that can be provided to regulators, for instance, to say, well, if we set up a site with this technology, this is the expected performance we have, and that can be used as a record from the regulator. So emissions monitoring, it depends on so many different factors, and the siting tool combines all of these factors into one meaningful deployment method. So what are those factors? The siting tool takes all of these input parameters, and I will introduce all of them shortly in the tool. You have a site layout where you locate all of the different potential sources and their heights. You pull in weather data from the previous year. There's a detection model to determine whether or not those conditions and the sources and the layout provides gets you a detection or not. And you provide an emission profile to say, well, what emission rate am I interested in? And it also considers what is the sensor spec that I have and how it impacts detection sensitivity. So it takes all of those inputs, and then it runs a simulation for every hour from every source to determine whether or not emissions were detected from each of those sources based on all of those things. And once it runs through that simulation, it does some calculations to determine these KPIs of coverage and time to detect for every potential emission source. So without further ado, I will pull in the siting tool. Hopefully all this works as expected. And okay, so you should be able to see the siting tool on my screen now. So to start, we've got kind of the site itself. So you can give it a name. You can go to the location by entering latitude and longitude. You can give it a name. So that's a simple way of getting to your site. There's another way to bring up the data. So I can upload a siting the same way, which is basically the same as what I just did there, but it shows you, this is a preset site that I'd like to demonstrate with. So I gave it one source so far, but you can see here is the satellite image. I can choose whether to bring in Google Maps or an open source Esri world satellite image. And then I can add nubospheres. I can add other types of sensors, CUVAs, Mach sensors, Sentry, and I can add specific emission sources on here. I can also fetch the weather data, so I just click into this. It's pulling in weather data, both wind speed and direction. It also pulls in shortwave infrared for the Kuva camera for the last year, so this shows me the exact time, the date range that it pulls it in, and this is hourly weather data. And then this is kind of the metrics section where I can choose what emission rate I'm interested in. I've got a recompute detection timing button, which basically runs the simulation to say, to determine the metrics. And then I have a section on notes down here, but also I've got a list of emission sources and sensors. So let's just go ahead and lay this out just for initial utility demonstration purposes. So this is the first piece of equipment potential source that I've added. So this is a wellhead. I've given it the label of WH1, and it's at 1 meter height, and I can save that. I can add more sources here. So I can say wellhead and call this wellhead 2, add a meter as well, and a third wellhead. So now that I've laid those out, I can come in and add some nubospheres. And what you can see from this wind rose is that the prevailing wind is from the south. So typically we would be sighting more spheres towards the north if we wanted to have more detections. So we'll start with 3. And what I'll do here, I'll compute the timing, the detection timing, run that. So you can see I've got a coverage of 47.3. I'll get into what all these mean in a second. You've got a probability, a 50th percentile or median of a 1 hour detection, a P90 of 29 hours, and all of my sources were detected in this period. So I can move these around and you'll see these values change. So, but just by moving one sensor to another location or 2 sensors around, I've gone from 47 to 56%. And my P50 is now gone to 0, and my P90 is at 32. So this all happens relatively real time as I'm moving these around. So by moving one to the south as well, I've gotten a different metric there. So that's come from 30 down to 13, even though my coverage didn't change. So the last items I would show on here as a UI tool, I can draw some lines on here to show and to optimize the placement of these. It takes a minute, so I'm not going to run that today. But the other things that can be done, I can save this sighting. I can export a PDF of what the results are. And yes, I can do all of those. So coming back into the presentation to describe kind of how we got to those values. So we have to have a model behind it. And so how did we come up with this model? What is the model? For the nubosphere and nubocentries, what we did was in collaboration with John Albertson from Cornell, we developed the rigorous dispersion model. It's been validated through field testing at METEC and TADI, as well as other facilities. And if you'd like more information on the model itself, you can find it at on GitHub at the scope tool repo, which is at this URL. And then for Kuva, we did a similar thing, but it's a little bit different. It's not a network of sensors that we're evaluating. We're actually evaluating just one camera to see whether or not it can detect things. So what we did was, we've tested it at numerous test facilities, and we've developed a model to determine the expected detection range based on ambient conditions and emission rates. I will get a little bit more into that later, but for the nubos, for point sensors, Here's are some illustrations of the variables that impact detections. So this first one shows you a moving source height. So this will go up and down. And what you can see is this green line is the detection contour for the Nubo spheres. And so this is a 1 kilogram an hour leak at a 3 meter per second wind. And so as you can see, as this source goes up, the plume rises, of course, and we've got a sensor located here at 100 meters downwind. Once this goes up above 6.5 meters, then we don't detect the emission at 100 meters distance, but for a 1 kilogram an hour leak and 3 meters per second wind. So similarly, for when we adjust the wind speed, you can see with stronger wind speeds, the plume contours are much smaller. But then at lower wind speeds, that plume extends well beyond. So this is again, 1 kilogram an hour leak, 3.5 meter source, and changing the wind speeds. So this is the sensor again. You can see it's green there. But when a very strong winds, what do we have? 6.4 meter per second winds, average wind speed as well. That's kind of the cusp of when emissions are detected at this distance and under those scenarios. And lastly is the emission rate, and this one's probably the most straightforward. The higher the emissions rate, the bigger the plume. Okay. So now let's get back into the detection metrics. So I will flip back over here. So as you can see, the coverage here is listed as 57.5. And so what does that mean? So this is from a single wellhead. We basically go through and look at every source and determine, did an emission get picked up at the given emission rate in every hour of the previous year based on those conditions. So the source coverage is the share of the year when a leak from the source would be detected. So the other 41.7% of the hours, the ambient conditions don't result in expected detection. And then the coverage score is just the average of all source coverages for all sources. So green is when it was detected, and this is split into individual hours. It's kind of hard to see because it's a full year, 8760 hours. But what does all this mean? So what is a good coverage score? I mean, this really depends on use case and customer objectives. So generally, we prefer we target a higher rate coverage for operational excellence than we do for site level inventory. And that's because we can extrapolate. For site level inventories, you can extrapolate a value like 30% to a full year fairly well. Whereas for operational excellence, yeah, you might want to have a higher coverage so that you can see more of the leaks quicker and go and fix them quicker. So for operational excellence, that coverage that we target is somewhere around 50%, whereas site level inventory is more like 30%. When you compare that with quarterly surveys, they have a coverage of only 0.05%. You've got a snapshot 4 times a year. So all that said, continuous monitoring in this scenario provides 1,200 times greater coverage than quarterly surveys. Okay, and then, so that's coverage. Time to detect uses the same data. It's basically saying, okay, we've got everywhere that we have a green detection, that would be a time to detect of 0, saying it would have been caught within the hour that it occurred. And then we fill in all the blanks of the white spaces. So here we've got, P50 time to detect of 0 and P90 of 13 hours. But taking a snapshot, a 3-day period from that full year, you can see each of these bars. We've got 24 hours on each day, of course. The green ones are when it was detected, and then the non-green ones give you a number showing you how many hours until it was detected. As you can see, it kind of counts down. These would have been white in the previous slide, and we just fill these in showing you how many hours until we actually get another green detection. So for this 3-day example, our median, our P50, is 2 hours. So half of all emissions are expected to be detected within 2 hours. And similarly, for our 90 percentile, that's saying 9 out of 10 emissions are expected to be detected within 14 hours. So there is one more metric that has recently been introduced, which is this duration specific, because as you can see, 0, that's low for the P50, and 14 for P90 seems a little high, but that's not to say that, every leak needs to be 14 hours to detect it. It's what we've done here is we've come up with a way to say, well, what duration emission do you expect from your sites? Is it 1 hour? Is it 5 hours? And so what you can do is you can choose a specific duration, and then I can recompute that, and that will give me the probability of detecting leaks. If every leak was 5 hours, we would have a 79% chance of detecting it if in these scenarios at this site. So coming back to the full year distribution from this example, this is a histogram basically showing the distribution of time to detect. As you can see, the coverage 58.3 are caught within the same hour, and then it trails off with a long tail here. And so the P90 is showing at 14 hours. And then if we say, if all leaks were 5 hours, 78% would have been detected. So this is the percentage of leaks that are detected within the user-defined time. Okay. So now that we've gone through a simple site there, we'll increase the level of difficulty a little bit. And so what I can do here, I can just upload the next site. And so if I show the Google Maps view, and I scroll down a little bit, you can see we've got all of these sources listed. So we've got a third-party meter, and this is something that we would do with customers, when we lay out a site. So we would ask, what sources would you expect emissions to come from, and what is their height, what is their name? So we've got a third-party meter, a pipeline, well heads, we've got a compressor package, we got a couple of separators, and we've got tanks. And as you can see, the tanks, they're 7 meters tall. So you can put in different heights, and they're all listed down here to show you kind of a summary of everything. So I open this up, and then I fetch the wind, the weather data. And again, this is an interesting one where prevailing winds are mostly from the south. And I can see when I show the coverage, only So the coverage score for everything is 48%, but I do have a couple of yellow icons here for sources, and those are listed here what that means for each source. So if it's between 20 to 50%, it would be yellow. And these tanks are showing as 25, 24. The wellhead's at 49, so that's pretty close to 50. Same with this third-party meter. But our tanks aren't that well covered because of their height and their proximity to the downwind side of the site. And so this fence line sensor, this Nubo sphere, doesn't do a great job of detecting these all the time. So this is where we can start introducing other technologies like sentries, and I can put those right on the tanks. And I can add another one. And then what you can see here is now we've gone to 56% covered, and my tanks are now covered over 50% here. So this gives us a nice coverage score of greater than 50%. Everything on site seems to be at 50 or close to and above. And I would call this a well-covered site. If I wanted to check out my time to detect values, so I've got my P50 is 0, so at least half are detected within the hour, and 90%, 9 out of 10 are detected within 11 hours. And if I wanted to see what, if all my leaks were 3 hours long, I would expect to detect 76% of them. If they were all 6 hours long, for instance, 84%. So that distribution is very skewed, as you're aware. And this is kind of something, 84% of 6 hour emissions detected is quite well covered. Okay. So if I come back to the presentation, and bear with me. So then let's look at one other site here. If I refresh, okay, sorry, just about left the meeting. Okay, so here's a somewhat more complex site. And as you can see, we have a number of tanks. These are 9 meters tall. We've got a number of separators here and treaters. We have a flare. We have some piping. And well, let's look at adding a CUVA camera, see what happens there. So I've got an emissions rate of 5 kilograms an hour. And if I place one CUVA camera here and I compute this, you can see there's 6 sources that are never detected. There's some that are detected very seldomly, 15%, and then there's a bunch that are at 0. And same, okay, tanks are at 15. So one CUVA camera would not cover this full site, but maybe let's try adding a second one. Okay, so then this is showing that we've got 36% coverage, and our P50 is 4, P90 is 14. And I can move these around, see where might be the best location for everything to be detected and covered. The flare, it's 15.9. It's not that well covered. Knowing that CUVA cameras only work in the daytime, I mean, you're maximum expected coverage would be 50%, of course. And so 37%, that's pretty good. If I increase this to 10 kilograms an hour emissions, then that flare gets much better coverage than it did at 5. But similarly at 2, these are pretty small rings. So how can we, how are we going to enhance this site with other sensors? And I can come, well, let's just say we've got 2 cameras. This gives us coverage. So I can take some notes here. 2 Cuvas get you coverage of 37 and a P90 of 14. So then if I get rid of these and I go to see how spheres, if we add some spheres here at 5 kilograms an hour, I can drop these around. So I'm still at 34. I don't have great coverage of all these tanks. They are pretty high. Maybe I'd add another one over here to help pick those up, pick up the tanks. So that gets us to 40.8. Not bad, but not great. So my other options now are I can add a Cuva camera or I can add sentries. So if I add a few more sentries, I should be able to get, cover the rest of these tanks. That gets us to 46. So we still have a couple of tanks that aren't that well covered. And the flare, of course, is not going to be covered by much other than possibly a Cuva camera. So by adding 4 sentries, this goes up to 49. And I'm going to remove the sentries now. And then I'm going to show you how a Cuva camera can enhance this by having it monitor the tanks. So that jumps it up over 50% to 53. And we get a P90 of 11. So without the Cuva camera, we're at 40.8, so 5 spheres. We have 40.8 coverage and a P90 of 28. And if I add one Cuva camera, that coverage goes to 53. And the P90 drops pretty significantly as well. Coverage of 54, P90 of 11 hours. So this is just a way that you can see how multiple technologies can complement and enhance the others. Similarly, if we wanted to see how metal oxides would detect this, I'm just going to lay this site out with our metal oxide sensors. So Sensirion has had metal oxide sensors in the past, but we have moved away from using them. So now that I've got those laid out, I'm going to remove all of the other equipment and see how that looks. So by double clicking, I can remove these spheres. So this is showing us that, the low to the ground equipment is well covered. 42s. And then the higher stuff, the tanks, they never get detected. So we've got 14 sources that are just never picked up because of the higher MDL, minimum detection limit, of the metal oxide sensors. So that takes us down to a coverage of, so if we have 5 machs, coverage of 22.6. These values are only calculated from the things that are detected. So the fact that 14 of 28 sources never detected. Okay, so that covers the sighting tool demo itself. And now I think we'll leave some time here at the end for questions, and I will wrap up the presentation. So we've gone through the last two with an upstream production site with spheres and Sentry, and then the last site where we tried all the different technologies. So how do you get your sites evaluated using the sighting tools? So please reach out to your customer success manager or your key account managers within Sensirion. If you'll have to share your lat long and a plot plan or a list of potential sources along with their heights. And then this is really a collaborative effort to lay these things out to make sure that you can achieve the goals that you'd like to. Obviously, there are budget constraints, but we will present options and share performance for each of them, and then we can provide a quote after we've gone through that exercise. The other thing to mention is there is a source available public tool called Scope, which I mentioned earlier in the GitHub repo, which you can try out for yourself. All you have to do is put in a minimum detection limit. This is for fence line monitoring only. And you can play with that. So without, just to summarize everything that we've gone through, we've mentioned, and you should now know what the sighting tool is, what it does, how it works, the variables that impact detection capability, the performance metrics coverage and time to detect, and how to quantitatively compare technologies and configurations, and how you can get your sites configured and evaluated. So that seems to be right on time here. And let me just jump back to the questions. So feel free to pop your questions into the questions area, and I will get to them. So we have a few questions here. So what is the assumed height of the sensors? So for Nubo spheres, we assume that the height is 1.5 meters. That's our standard installation. It goes on a mount, a standard pole mount, and generally all Nubo spheres are installed at 1.5 meters. You can imagine if they were much higher up, yes, higher sources would be detected, but the fence line sensors are all on standard sources, standard stands, and the spheres, the sentries, they get installed in the tool. They're assumed to be at the height of the source. So those are our close proximity sensors, and they get assigned to the height of the source near them. Okay, so what coverage should I target if I want to achieve site level reporting, OGMP 2.0 level 5 reporting? So generally that should be around 30%. There is some math behind it that, as I mentioned, does extrapolate beyond what is detected and quantified to the times that we know we don't detect it. So that's kind of the flip side of this. There are times that a site will not detect things because the wind is not blowing in the right direction. However, we know that the wind is blowing in the wrong direction, and so we know that we don't know what's going on there, but we do know what's going on when we did detect things, when the wind is blowing in the right direction. So we're able to come up with a comprehensive site level inventory. There is a bit of a uncertainty around that, but there are papers out there that describe this process. So 30% is a good site level coverage for OGMP 2.0. And then last question here is, should all sources obtain the target source coverage or just the overall score? So are we looking for the average across all, or are we looking for the minimum across for every source? And that really just depends on what it is that you're trying to do. So some regulators, if they're saying you have to monitor tanks continuously, you may need to obtain at least a 25% coverage on every tank. But if you're just doing this for operational excellence, for instance, you may be willing to have a lower coverage on your wellheads, for instance, than you do on your tanks or you do on your separators. So it's more or less a preference that is determined from a conversation with customer success and going through this exercise. But I wouldn't say that you always need to have everything at a minimum. However, there are some scenarios that there are. Okay. Any other questions out there? I'll give you another minute. I will answer any. Well, okay. Okay, there is one more. How do I see that? Oh, there it is. Okay, good. Thank you. So how does the sighting tool differentiate between venting, fugitive, and methane slip emissions? Is the model optimized for certain emission source types, or are there limitations for others? So great question, Guy. The methane slip from combustion of compressors, that's generally ignored from this. That those exhaust emissions are super hot and they typically just vent straight up and over. So those are omitted from the emissions. Whereas venting and fugitives, that is within the sighting tool, it's not differentiated at all. We do apply specific venting, permitted to emit or thresholds for each source. Once you do a deployment and you have them have a CS deployment, what you can do is you set a threshold for when you want to be made aware of certain emissions, and you set a threshold for each source to say, well, we know this is a venting source, so we can set that to whatever 1 cubic meter per day. Anything below that, that's fine. I don't want to know about it, but anything above, we do. However, for the sighting tool specifically, it's not necessarily taken into consideration. We treat emissions as long as they are low, not hot exhaust. We treat them with the same dispersion model. So it is optimized for more or less low pressure emissions of natural gas, basically not combustion products. Okay, we've got a couple more. All right. Could you list the Nuvo Sentry Could you just use the Nuvo Sentry for site level emissions? Operational excellence use cases near the likely major leak, venting sources, or do you always require minimum coverage? No, we can use Sentries only is a great application. And absolutely, those can be used for site level emissions or operational excellence. It's one of those things. I mean, that's our only intrinsically safe device. So offshore, that's a scenario where we would only use Sentries. But even smaller sites, if you're trying to keep your costs down and you don't have a ton of equipment that you want to monitor, for sure, Sentries could be used for either operational excellence or site level emissions inventories. It is a great option for both, but with expanding complexity, you get more the need. One Nuvo sphere can do more for you in a lot of scenarios than one Sentry. So there is an optimization for that as well. Thank you, Michael. Hopefully that was helpful. Okay. I don't see any other questions. Oh, one more. Zach. When calculating detection, how do you define detection? So detection, it is when the, so this has been validated through performance testing, but what we found, it is when the plume boundary layer, so from those animations I showed, it's when that boundary layer exceeds the minimum detection limit of the sensor at the distance away and the downwind direction. So the dispersion model basically determines a distance away from each source that it can be detected if your sensor has an MDL of whatever, 0.3 ppm in this case. And this, because we're using hourly average weather data, we've assumed and validated that to be an accurate way of determining detection. So it is, as you say, exceeding the lower detection threshold, but it has been validated to show you that it does kind of spike above the baseline of the emission of the background emissions. Okay. Any other questions? All right. Well, if not, I appreciate your time. Thank you for joining me, and hope to hear from you. If you have any questions, you can let me know. Otherwise, you can talk with your key account managers or customer success folks. So appreciate your time, and chat soon. Thank you.